Hello, everyone. Welcome back to the second lecture in this lecture series, where Madhu is going to be speaking on topological quantum field theories. Over to you, Madhu.
Hey, thanks a lot, guys, for coming back. I see I've managed to cut the standing strength to half of what it was last time. So, yeah, okay, cool. So, so this lecture is just going to be some geometry, right? I'm not sure how fast we're going to move, but let's just try and move in a way that everyone's sort of keeping up with what we're discussing. The last time we discussed some general properties of topological quantum field theories. We took the sort of path integral. We started with the path integral of theory, and we had certain requirements of a topological quantum field theory. And we saw that those requirements essentially establish the metric independence of correlation functions and so on, right? Part of this discussion much later on is going to require that we be familiar with geometrical facts about how to formulate topological quantum field theories in a more mathematical framework. So that's why we started talking about fiber bundles last time. So my plan today is to talk about fiber bundles and hopefully get to, I definitely want to get to at least principal G bundles today. One thing I want to know from all of you before we finish today, so just take some time and think about it, is I know that a sequence of lectures that's just math is going to be kind of dull and uninspiring to most of you because we're not used to thinking in this way. So one possibility is that we can do one math lecture, one physics lecture, and back and forth, so that things kind of stay a little interesting to most of us at least. So just think about that and let me know after the lecture today. Okay, so we already saw the definition of a fiber bundle. I just want to go over it briefly before we continue. So we start off with a manifold M, right? And let's say we have another manifold F, which we're going to call the fiber, right? So M is the base and F is the fiber. So a fiber bundle E over the base space M, that's why it's called the base, with a fiber F is locally a direct product of M and F, okay? So just as in the case of Riemannian geometry, where locally we have flatness, right? In the theory of fiber bundles, locally we have products of manifolds. Okay, that's the key distinction to keep in mind. And the interesting thing is that if we have the property that locally our manifold is a direct product of M and F, what that doesn't specify, however, is the global topology of the fiber bundle, and that's really where the interesting stuff begins to happen, right? And we saw that there can be kind of interesting things happening. We saw that there can be interesting things happening when we have this requirement of local triviality, but sort of globally it couldn't possibly be non-trivial. The simplest example of this is a Mobius strip, which is just the locally it just looks like the product of a circle and an interval, a unit interval, but globally it can be kind of twisted, right? So what we have to do is we have to specify, in addition to the base manifold and the fiber, we have to specify transition functions. And transition functions, they tell us how the fibers match up in overlapping regions of charts on the base. Okay, so really the transition functions have non-trivial information about how twisted the product is. When I say product, I mean product I'm referring to between M and F, right? So the transition functions are really the guys that have the information about how the product is twisted. This is one of the reasons why fiber bundles are sometimes called twisted products. Okay, so that's the mantra, right? Locally trivial, globally non-trivial. And we saw that we have this theorem also we saw last time, which we'll prove today, that any fiber bundle over a contractible base, such as Rn or Sn, after you've removed the point, is trivial. Okay, so you basically need a non-trivial base in order to, so when I say non-trivial base, I mean a base manifold with a non-trivial topology in order to have a non-trivial fiber bundle. Incidentally, when I say a trivial fiber bundle, what I mean is just that globally it is just a product. Okay, and all of the transition functions are just identity. Okay, we also saw the definition of a section of a fiber bundle, and what a section does is it assigns a point in the fiber for every point on the base. Okay, so locally you can define sections on patches. The question of whether or not we have global sections or sections over the entire base manifold that are non-trivial over the entire base manifold remains to be seen. Okay, so this is a sort of little cartoon where we have points on the base here, and what a section is doing is it's assigning a sort of a value in the fiber for each point in the base, right? So that's what this cartoon is supposed to represent. So what we want to do is we want to do this a little formally, and the way we do it formally is we define a projection from the bundle onto the base manifold, and the projection itself basically the inverse image of the projection tells you what the fiber is over a particular point. Okay, so not inverse image. What I mean is the pre-image of a point is really the fiber over that point. So yeah. So for when I have, let's say I have like a local coordinate patch on the base manifold, and I consider the pre-image of all the points on this coordinate patch. The part of the definition of a fiber bundle, which we'll see the formal definition right now, part of the definition is that the inverse image of every point on in a local coordinate patch is a subset of E, which projects down to M under the projection. So what we have really is this: we have an isomorphism between patch times F, where F is the fiber and UI is the patch. Patch times F is basically the statement of it being locally trivial, and pi inverse UI is just the pre-image of any point in that coordinate patch, right? So when someone gives you an isomorphism like this on a patch, it's called a local trivialization. Okay, fiber bundles are said to be locally trivial. This is what it means. This is the content of that statement, that there is an isomorphism between UI times F and the inverse image, the pre-image of UI. Okay, so now we're going to talk about the formal definition, right? This is the way that mathematicians will usually define it. By the way, please interrupt me if there are any questions so far, or henceforth. Are there any questions before we get to the formal definition? This was stuff that we saw last time, but if there's any questions, we should get done with it now.
Can you give example of that isomorphism for the Mobius strip case? Just some small example.
Yeah, I don't. So I can. How about I do that at the end of the talk? Okay. So you know, the Mobius strip is a nice example because you can work it out completely, right? But yeah, I'll give the example to you at the end of the talk. Okay. Good. So and I think we'll also see examples as we go. So the formal definition of a fiber bundle is that a fiber bundle is denoted E. It has a fiber F over a base manifold M. So E is a topological space, right? And equipped with a projection E that maps E to M that is locally trivial, right? We've already seen local triviality. That what that means is that for any point in the base manifold, any X belonging to M, there exists a small neighborhood of M, right, UI, that contains X, and there exists an isomorphism phi I, which maps UI times F to the pi inverse of UI, right? So it maps the direct product of UI, which is a small coordinate patch, and F, and it maps that into the pre-image of UI. And it does so in such a way that this is basically a consistency condition, that when I take phi I, right, phi I takes two arguments, right? One comes from UI and the other comes from F. Okay, so the X here comes from UI and F, small f, comes from capital F. So when I take phi I of this pair, what it does is it maps me to some, so phi I acting on this guy is some point in the pre-image of UI. Okay, so it's some point in the fiber bundle. Okay, and when I project that down again, then what I get is just the base point that I started out with. Okay, is this consistency condition clear? What I'm doing is I'm feeding, so phi I is a map from UI times F to pi inverse UI. So phi I acts on a pair, right? One comes from UI, the other comes from F. And this whole object, phi I acting on this pair, is some point in pi inverse UI. And when I project that down to the base manifold, then I just get the point that I started out with. Okay, so that's the consistency condition. And the consistency condition is really what ties phi I and pi together. Okay, so I've drawn a little picture here, which is supposed to sort of help understand.
Madhu?
Yeah.
Yeah, just to clarify. So this phi I of x acting on xf, this gives a point on the fiber, right?
No, so it gives a point in the total space. When I say total space, I mean E. Okay, so it gives a
this
point.
pi inverse map is this is the section, right?
No, this is not a section. So pi maps E down to M. Okay, E is the fiber bundle, and
Right.
M is the base space of the fiber bundle.
Right.
So when I say pi inverse UI, what I mean is I take some small coordinate patch on the base manifold, right? And I look at all of the points that under pi would fall into this this guy over here. So this is really what pi inverse UI.
So it can be any point, like it may not necessarily be on the fiber. Like when we act phi I on some point xf.
Right.
Yeah. So and also, can you once again show me the definition of section?
Section. Okay, good. So a section is a section S of the fiber bundle E assigns a point S of X, which belongs to F for every X in N.
Okay. Yeah, thank you.
So there's an important distinction between a section and a projection. Okay, a projection is a map that shoots downwards. Okay, a section is, let's say there's this space over here. Section shoots downwards. The point is that any point here on this fiber, all of those points are going to map down to X. Okay,
I think you meant the projection.
That is projection, right? Yeah.
That is projection. Sorry. Did I say that wrong? Sorry. I meant a projection is any point on this fiber is going to map down to this point X. Okay. So the projection is not, it's not invertible. That's an important point, important distinction. Like it's an important point to understand. The projection is not an invertible. So when I write pi inverse, when I write something like pi inverse, I don't mean the inverse of it as a function, because obviously you cannot have an inverse when all of these points under pi map to X, right? Because if I write pi inverse of X, what does that mean? Which point do you go to? So it's not invertible. When I write pi inverse, that's why I keep saying the pre-image, right? When I say pre-image instead of like inverse, what I mean is the set of all points that should you act on pi with, they will drop down to X. Okay.
Yeah. Okay.
Whereas a section, what it does is it starts with a point on the base manifold, and it associates to each point in the base manifold a point in the fiber, one point in the fiber.
Okay. Yeah. Thank you.
I hope the point about pi. Sorry, I should have made this clear. Perhaps the point about pi inverse should be clear. I don't mean it is inverse as a function, right? Because it's clear from what I've said over here that since all of these points are going to map down to X, there's no way to say what the inverse of this function. It doesn't make sense, right? But what you can do is you can say there is a set of points such that when I act with pi, it all falls down to X. That is the pre-image of a set under a map, right? And that's what I mean when I write pi inverse. Is that clear?
Yeah. I was a little confused. Now it's fine.
Good. Okay. So now what I want to do is I'm just going, this is a small picture here. Okay. And I hope in general, I found that drawing pictures like this helps me. I don't know if it will help you, but if you should find it helpful, then please cite me. Here we have a base manifold M. Okay. And these guys over here are small coordinate patches. Let's say uj, this is uj, this is ui. Okay. So when I write pi inverse ui, what I mean is the pre-image of ui under the projection map. Okay. So the set of all points that under the, or this set over here is the set of all points that under the projection fall down here inside ui. And same with pi inverse uj. Okay. Now, what we required is that there is an isomorphism between the inverse, the pre-image of ui and ui times f, right? So that is indicated by this arrow with phi I over here. Okay. And same with this bit over here, the pre-image of uj, right, and uj times f. Okay. Now this diagram is a little misleading because these don't really overlap. So there's no sense in which you can have a transition function. Okay. But you can imagine bringing these guys closer. Okay. Such that there is an overlap. And when there is an overlap, right, then you will have transition functions. And those, so basically the transition function is basically saying that there has to be some consistent way in which these two pictures merge when there is an overlap. Okay. And the phi ij's, these are precisely the transition functions, right? The transition functions really take you from here to here to here to here. Okay. So that's phi ij. So that when I write phi ij, what I mean is phi j. So the order in which it is acting is this correct?
Isn't your arrows in the
is it in the wrong
direction?
Yeah, I think it might be in the wrong direction. Sorry about this.
You can just change. Yeah.
Okay. So sorry about this. So does this work?
Maybe
No.
you want to act with phi in inverse first and then phi j after that. I mean, I don't really know in which order do you want the functions to work.
Yeah. Okay. Yeah.
I think the convention is different for physicists and mathematicians. I think the how the composition works, whether the left is the first or the right is the first, I think that's a convention that you can just choose that.
That's right. I mean, so right, with this current set of arrows, basically what's happening is that I act with this guy on the right, which is kind of, I don't want to do that. So let's not do that because that's going to cause some confusions. Let's stick with the original arrows because I think I was onto something back then, and let's work it out now. Okay. So what I want to do is I want to go from I want to do phi inverse j, right? Inverse j that goes here, then phi. What am I doing? Hold on 1 second.
Looks like you have the left action, right? I mean,
yeah, that's what it looks like.
Yeah.
Madhu, the arrows that you're drawing is actually from pi inverse of uj to pi inverse of ui. The phi ij's.
Right.
So it's not from uj cross f to ui cross f. It's from pi inverse of uj to pi inverse of ui. The arrows.
That's right. Yeah, I need to have it like this, right?
Yes.
Is that right?
Yeah.
Yeah.
Phi j. No, but now it will be phi j inverse and phi I.
Phi j inverse phi I. That's right. Yeah. Sorry about this, guys. I'll yeah, this looks correct to me now, but it may be wrong. So I'll fix it and figure this out before next time. Okay. But the basic idea is that your transition functions sort of tell you how to go from one patch to another patch when you're talking about the when you're talking about the full bundle. Okay.
So just one small thing. So
yeah,
when you have the functions phi ij, you
right.
write the functions phi ij after you go to this open set into F structure. I mean, you don't add them on the pi inverse of the base space itself.
Yeah, the phi ij's can be thought of as just acting on the fibers themselves, right? It's
exactly.
Kind of
so you first go into the product structure.
Yeah.
And then the phi ij's act on that form.
Right.
Oh, so, Sorry, the phi is a map from U cross F to pi inverse. So pi inverse has to be the opposite map. So the domain is actually pi inverse of Uj.
Is that right? Okay.
I think Madhu's video is stuck or something. No.
Right. Are you? Yeah. Hold on.
Pi inverse of Uj is Uj cross F, right?
Yeah.
By isomorphism. Yes.
By isomorphism. That's right. Yeah. The phi. So the transition. So the transition functions, what they should do is they should really be acting on the fibers. Okay.
Can you scroll back up and just for a second show? Yeah, so I think what Anish was saying was right then. The way you have phi ij, phi I composed with phi j in inverse, it's going to act on the pi in inverse.
Right.
Of Uj and go to pi inverse of Ui.
Yeah. So, but the thing is that by isomorphism they're the same, right? Like this guy and this guy. Yeah.
Sure, but it seems it's fine now
because
that's the way the phi
actually. So the thing is that because these guys, I mean, so this is isomorphic to this and this is isomorphic to this. My earlier arrows were fine, I think, right? So I'm just going to draw it like that because it looks better. But you get the point. The point is here that the point here is that the transition functions are maps from, it can be thought of as maps from like just F to F, okay? And they basically tell you how to piece together the fiber when you're on an overlap.
You said something about like, you can only apply this when there is an overlap, but the picture that you have drawn, there is no overlap.
Yeah. So this picture is misleading. But my point, I mean, I didn't want to draw it like that because it would look like a mess. But basically, you have the game of transition functions arises when these two sets kind of overlap with each other. Okay, and everything is happening in the overlap region.
I see. Okay. And yeah, I somehow thought that you would say that even if they are not overlapping, you can do something so that they are overlapping and then apply this.
No. So what I was saying was that, like, if you consider two patches that are disjoint, like if I have one patch on one side of the manifold and another patch on another side of the manifold, this does not make sense, right? But what I can do is if I bring them close together and they overlap, then in that overlap region, right, this sort of thing is at play. So these maps are this sort of map is defined only in the overlap region. Yeah.
Maybe I can just add to that. So I mean, this is nothing new. It's the same thing that we have even on usual manifolds when you have two charts and then you have this overlap and then you have sort of a coordinate transformation that takes you from one chart to the other. So it's the same transition function, but here you have an additional subtlety because on each of these charts you have two fibers, right? And these fibers, they need not correspond to the same, the fiber points need not overlap. So you need a map from the fiber to the other fiber as well. Right. So this basically is a slight generalization of that.
Yeah. So you can imagine, for example, just setting all the fibers to be a point. Okay. So if you just forget about the fiber, this is the usual story of transition functions on a manifold, right? And you'll have something that looks like this that arises in that context as well, right? Just when you have an ordinary Riemannian manifold overlap of two charts, basically the point is that the physical point that you're describing has to be the same point, irrespective of what chart you use.
Right.
The same way, the point on the fiber is basically the same point that and that's what the transition function really accomplishes.
Right. Yeah.
All right. So the transition functions typically form the set of transition functions forms a group G, which is called the structure group of the fiber bundle. Okay, and it satisfies the following what are called co-cycle conditions. That phi I. So here the subscript refers to the subscripts here refer to the indices labeling the charts on the base manifold. Okay, so when I have just phi I, which is like from UI to itself, it's just the identity map, right? And when I have a three-way intersection of sets, then phi ij, phi jk should be phi ik. Okay. And now what we're going to do is we're going to these consistency conditions are easy to work out. Intuitively, also they're clear. They basically it's just you might think that what if I had a four-way intersection? It turns out that these two are sufficient to sort of establish all of the rest. Okay. So what we're going to do now is we're going to play around with this idea a little bit. We're going to perform various constructions on this stuff that we already have. Okay. Are there any questions? Okay. All right. Good. So now we're going to perform a few.
Hi, Madhu.
Hi,
So is there any so with the structure group G, is it is there any problem with it for local and global cases, or is it?
What do you mean by that?
I mean, for example, let's say you have a local trivialization that you said, but globally, let's say it's not a trivial bundle.
Right.
Then the G is the same. I mean, does it have anything to do with local or global properties?
No. See, the structure group is purely local data.
Okay. So it's basically directly comes from the definition, right? Because I have all the phi and pi fixed from the definition. So structure group is already fixed.
Given exactly. Okay. So you see that like over here, for example, we define the transition functions in terms of just local stuff, right? This manifold could be huge.
Right.
Which is just local data.
Okay.
Later, we'll take the structure group to be more recognizable things. Like when we study vector bundles, for example, we will take the structure group to be just a general linear group, right? You know, you can take it to be, for example, a unitary group or whatever you want. So, yeah. Are there any other questions? Okay. Cool. So now what we're going to do is we're going to sort of perform a few constructions. Okay. The first of these constructions, these constructions are really just to get you used to the thinking about stuff in this way. The first of the constructions is what's called a pullback bundle. Okay. Now you'll all remember that if you have functions that map one manifold to another, right? Then you can do certain things with the functions themselves. For example, you know that you can like pull back differential forms. You can push forward vectors, right? Does everybody kind of remember this? That, or at least know that it can be done and I can look it up if I want to, right? Okay, good, that's fine. So the idea of a pullback bundle is roughly the same, right? Let's consider a fiber bundle E over M, okay? I've written pi over here, there's a projection pi. And so this is a fiber bundle, and let's suppose that there is a function H, which maps a manifold, base manifold M prime to the manifold M. Okay. The idea of a pullback bundle is that we can really pull the bundle structure over M back using the function H to a bundle over M prime. Okay. And the way we do that is really by copying the fiber of E over each point X. So because of this guy, each point X on the manifold is now H of X prime, where X prime sits in M prime, right? And what we do is we just copy the fiber of E over the point X over the point X prime.
I think you mean that for each such x, which is of the form h of x prime, you can put the fiber that was on x to the
Fiber over
on,
x prime.
yeah, okay. It's
Right.
not that each x will be of this form.
Well, if I have a map between two manifolds, then why is that not true?
Well, the function might not be like an onto function.
Okay, all right, yeah. For each x such that it can be written as h of x prime, right? We have what we do is basically we copy the fiber over x onto the fiber over x prime.
So
Okay.
just to understand, like, so given some function x, you construct hx prime and then find out its pre-image under pi. Is that?
No. Okay. So what we do is x is a point that sits in M. Okay. Now, if I consider the pre-image of x under the projection, that's going to give me the fiber over x.
Exactly.
Right.
Yes.
So what I do is I copy that fiber over x prime.
Okay.
When x is equal to h of x prime. Sure. Do you want me to say that again?
Yeah.
Just... So what I mean is that for each point x in M, okay, like you can write x as h of x prime, okay, where x prime is a point in M prime.
Yes.
Okay. Now what I do is I consider pi inverse of x. Okay. Now pi inverse of x is just fx, right? It's just the fiber over x.
Exactly. Yes.
What I do is I associate a copy of that fiber to the point x prime.
Okay.
Okay.
Okay. Yeah. Okay.
So in more detail, how this happens is let's consider the we're going to understand the pullback as a subset of a particular a product. So let's consider M prime times E, where E is the original bundle, and there's M prime, which is the manifold that maps on to M. This guy, there's a function H which maps onto the base of E. Okay. Then let's denote a point in this product to be x prime and small e. Okay. Then the pullback bundle, which I will denote h star e, right? This notation is supposed to indicate, it's supposed to remind you of pullbacks of forms and things like that. Okay. E prime is the new bundle that you're constructing, and that is the pullback bundle of E, right? Using the function h, and that is basically given by the set of all points x prime comma e in M prime cross e, because sorry, there are too many e's here, x prime comma small e that belongs to M prime comma capital E, such that the projection of any point in E, any point E, small e, which sits in this guy, is given by h acting on x prime. Okay.
Yes, this is much clear. Yes.
Yeah. So this is basically like saying that it's like a subset of this product. Okay. And it's defined by this equation.
Madhu, just projection acts on the whole bundle, right? Not just a point in farmer in the fiber.
Yeah. Projection acts on, so E is a point, small e is a point in capital E. Okay.
Yeah.
So that means that when you project that point, what happens is it is projected down to the base manifold.
Yeah, I understand that, but I'm just saying projection acts on something like x comma e, and not just e. This is
no. So what I'm doing here is I'm E here denotes a point in the fiber bundle, not.
I see. Okay.
Okay. It defines a point in what's called the total space. When I say total space, I mean capital E. Okay. So small e is a point in the total space, right? Whenever I act with the projection on any point in the total space, it drops down
Okay,
to
okay.
the corresponding point on the base manifold.
Got it. Sorry. Yeah.
Okay. And when that guy is equal to H acting on some X prime, this is the definition of the pullback bundle. Okay. It's a subset of M prime cross E defined by this equation. All right. So of course, when I define a bundle, I have to tell you what the transition functions are. That's the important. That's like half of the information, right? So the transition. So if UI is a covering of M, okay, that is E is locally trivial, and UI and the phi ij's are the transition functions, right? Oh, sorry, is locally trivial on the patch UI, and phi ij's are the transition functions. Then H inverse of UI is the corresponding covering of M prime, such that your what's it called, your E prime or the pullback bundle is locally trivial. Okay, so you see what I'm doing is I'm using the function H to define a new bundle over M prime. Okay, and the transition functions of the corresponding pullback bundle are just the pullback of the corresponding functions, transition functions on E. Okay, you know that you can pull back functions, right? The reason you can pull back functions is because you think of functions as like zero forms, and you can pull back forms. Okay, if that's something that you're more used to thinking about it that way. So the transition functions of the pullback bundle are just the usual pullback of the functions under a map, right? So this is how you would define them. Phi prime is just defined like this.
Now hold on. Okay, so here I thought that the phi ij's are not just functions that act on the base space, right? So when you write phi ij prime of X prime, I don't quite understand that, because isn't phi ij meant to act not just on
sorry.
base?
Right. So sorry. So this is kind of misleading. What I'm saying is really the phi ij is corresponding to the point X prime.
Okay.
This is a bit misleading, but what I mean is that X prime sits in, so X prime belongs to some UI prime, which is given by this guy over here. That's really what I mean.
Okay.
Right, because the transition functions, if I fix a point on the base, the transition functions are just maps from F to F, right? So that's really what I mean here when I write it as an argument, although perhaps it's probably not very good notation. My understanding is that this notation is standard. So.
Okay.
Madhu,
Yeah.
Perhaps a stupid question, but anyway, so let's say it's a long question. Sorry. So let's say you have two total spaces. One is E1, another is E2. Okay.
Right.
And then E1 is locally, let's say, M cross F, some M cross F.
Right.
And E2 is globally M cross F. I mean, E2 is exactly M cross F. So does this mean that I can always start with E1, which is locally M cross F, and pull it back to E2, which is globally M cross F? Because I just need a mapping from M to M that is already there, this H.
Yeah.
So,
I'm going to work out an example, right? And that's sort of going to, I think, address this question. But the point is that you can only have this sort of thing happening when H is a function of a specific kind, my understanding.
but in both the cases, base space is same, right? At least locally, both the cases, E1 and E2, I said, because E2 is the globally M cross F, and E1 is, let's say, locally M cross F. Then both the cases, M's are basically same. So H should be, somebody's.
Wait, so no, I just wanted to understand what you were asking. So when you say that M2, E2 is of the form M times F, why
it's globally?
Yeah, but why is that important? I mean, you could have just said that it's a map from M to M, and I have.
That's what I'm asking, because because U1 globally looks like U1 locally looks like E2, not globally. That's why I just wanted to mention. So let's say U1 is a total space which locally look like who knows, let's say S1 cross some R or something like that.
Yeah,
okay?
maybe that's a good, you can just think of the Mobius strip and the cylinder as a
Exactly.
complete example.
Exactly, Mobius strip and cylinder, right? Exactly, that's what.
Okay.
It would be a good example. Yeah.
So what he's saying is, if you have a Mobius strip, is there any way that I can pull it back to a cylinder? That's the question that you have.
Exactly. Perfect. Thanks, Anish. Yeah, that would put it in a good position. Yes.
But here, this is not about a map between the full spaces, right? Here, it's about how to build a new fiber bundle starting from an old one.
Yeah.
Yeah. So the question is, can you build a cylinder from a Mobius strip? Like,
Exactly.
is that possible? Like, because I have S1 to S1, and let's say one of the S1 has the Mobius strip, is a Mobius strip total space. Can I pull it back and get a new space, which is from a cylinder?
One of the yeah, sorry. So what I want to say is that, like, one of the consequences of this definition is that if M prime is the same as M and H of X is X, right, which means that it's just the identity map, right, then H star E is just the original bundle.
So I cannot do that.
So I would think that you cannot do this.
Oh, but from the first definition, is it obvious, this statement? I mean, the E prime H star, is it obvious, this statement?
Is this one?
Yes.
I thought it was obvious. But yeah,
maybe the definition of the transition function, the fact that
you can see
Probably.
that phi ij
that's what
prime is the same as phi ij with H, because H is the identity map.
Right.
So you have the same phi's.
Right. That can be the answer. Yes.
Yeah, but good question. Yeah. Okay. Are there any other questions?
I just wanted to say that you can have more than one X primes that map into the same X. So the same fiber will sit on all the images.
Points. Right. Yeah.
So so it can be like a many to one map.
Right.
Which is not even on two. So it can, I mean, the function need not be 1 or on 2, and the whole thing will just still go through.
Right. Yes.
Okay.
And that's I mean, this sort of thing is especially important when, for example, you're trying to build examples, right? So maybe one time I should just come with a bunch of examples. But if you're trying to build examples and you start off with like let's say multiple covering of an S1 or something like that, right? Then this sort of thing becomes important because at some point you go all the way around, you come back to where you started, right? But if you have like multiple a covering of S1, right, then the pre-image of such a point is going to be a set of points, right? So you're going to have problems like this. So yeah, I think this is an important point that Aditya is raised.
So is there anything that, I mean, we don't have, I mean, we don't have to specify anything about H, like, H has to be of a certain
kind. Yeah.
Any H will do.
Yeah, I think so.
I think it has to be 1-to-1, right? You need H inverse, right?
Why do you need H inverse? You don't need H inverse anywhere.
To pull back, right? If I have a function from M to, so the map is from M prime to M, and you have a function on M, right? And the way you pull back is through H inverse, right?
No,
you don't need the inverse.
You don't use it. You don't use H inverse. You use H.
You use H precisely like this.
Right.
Exactly
So the other
exactly
one.
the way he has
Right.
shown. You use the map H, and then you have a function from M.
Yeah. I agree. Sorry.
Whatever space it goes into.
Right.
Yeah. I agree. Sorry.
I have a question.
Yeah.
Phi ij are transition functions between UI cross F and use
That's
J
right.
cross F, right?
That's right.
How can you have them? I mean, here phi ij prime is acting on X prime. It looks like.
So
I mean,
so when I write phi I, so when I write phi ij prime, right? What I mean is that this is a transition function in the the pullback bundle. Is that the question? Or
yes,
you're asking about this acting on X? It looks like it's
yes,
acting on
yes.
X prime. Yeah. So the idea here is that what does a transition function do? A transition function is essentially if I fix a point on the base manifold, okay, a transition function is basically a map from the fiber into itself.
Yeah.
Okay. So what this is really telling you is that this is the transition function associated to a particular point. So you should think of these guys as you should think of this guy as something that sends the f prime to f prime.
Okay.
Okay, it's associated to a particular point. So I mean, maybe if we go back up to the definition of the transition function, right? You see, phi I is ui times f to pi inverse ui.
Yeah.
Okay. So nothing, nobody can stop me from just replacing this ui with an x and this pi inverse with an x. Okay. Right?
Yeah.
If I just replace this with like an x and I replace this with an x, then basically this is a map from f to so this is just a point. So this is just fx to fx. Right?
Okay.
That's what I mean. Okay. Are there any other questions?
One small question. So the structure, so you're saying the structure group doesn't change in the new fiber bundle. Is that correct?
Structure group does not change in the new
fiber group of the new fiber bundle is the same as the structure group of the old fiber bundle.
Yes. I think so. Yeah. Are there any other questions? Okay, cool. So now we're going to come to a sort of a new definition. Okay, we have the notion of homotopy, right, which is also something that some of you may have heard of. So we know that two maps H and G from M prime to M are homotopic, right? The new word homotopic. If there exists a capital H, okay, which is a map from M prime cross the unit interval to M, such that when we evaluate capital H at let's call this coordinate t, all right. So if we evaluate capital H at t equals 0, then we get H, and if we evaluate it at t equals 1, then we get G. Okay. Two maps are homotopic if one can smoothly change from one to the other. Okay, when you can smoothly deform the map from one point to the other, this is the way we formalize that notion. We say that if there exists another map H, right, which maps M prime times the unit interval to M, right, such that if I evaluate this bigger map at let's say time t equals 0, then I get H, which is the first guy, and if I evaluate it at time t equals 1, then I get G.
You also need capital H to be smooth, right?
Yeah, I would think so. I mean, like, yeah.
That is also part of the definition.
Okay. So this is the context in which I would say that two maps are homotopic, when you can like smoothly deform one to the other. So if I have like two spaces, right, and I have two maps, right, then is there some parameter along which I can smoothly go from one to the other? Okay. So now there is a theorem that if H and G are homotopic, right, then H star, which is the pullback bundle of E using H, and the pullback bundle of E using G are isomorphic. Okay. So just as an example, if M is a contractible manifold, right? Let H let the function H just be the identity map, right? So it just sends every point to itself, every point on the base manifold, which is a base manifold M, to itself, okay? And let the second map G be a map that sends every point on the base manifold to a specific point x0. Okay, the map that this map basically shrinks all of M to a point. Okay. Now these maps are homotopic. The reason these maps are homotopic is because I can write down a function H. Well, I didn't write it down. I can write down a function H that is the following. So H it takes x and t, and we'll define this in such a way that at t equals 0 it is x, right? So how do I want to write this? I want to write this as so this is a standard thing that people do. Hold on, it's
ht plus 1 minus tg.
t plus t x. Okay.
Yeah.
So when I sorry, so yeah, so let me just color this so you can see it. Okay. So this is what I've done is I've just written down explicitly for you a function capital H like we saw up here. Okay. Now I see that when I set t equals 0, right, this piece goes away and I just get x. Okay. And when I set t equals 1, it's only this guy goes away.
Can I just say something?
Yeah.
So, well, by assumption, you know that such a smooth function H has to exist, but H doesn't have to be of this form. In fact, this form won't even make sense because you're adding x to x0, and that is not a meaningful thing to do. X is not a space where you can, I mean, M is not a space where you can add things.
Yeah.
So probably this is a very misleading thing to write.
Yeah. Yeah.
The H you wrote there.
Yeah.
Because you can't really add x
points.
and x and y and things like that.
That's right. That's right. But
no, but the thing is that by assumption, such a H exists because you have started the first part says that M is a contractible space.
Contractible manifold, yeah.
So by assumption, you know that such a smooth HXP exists.
Right.
And that is enough.
Right.
Probably writing this way.
Yeah, this is probably not very. This is misleading.
I mean, it won't even make sense to add. It's like saying I add x and y on a sphere to get something else on a sphere. That doesn't.
Yeah. But Aditya, what you said earlier, like if instead of writing it as x0 and x, if you just write it as h times 1 minus t and g
still it
times
makes
t.
No sense.
Then it's a map. Then
it's adding functions.
I'm saying I'm adding functions, and the functions, the domain is the same, right? I'm not adding points. I'm adding two functions. If I write it that way, then it makes sense, right?
No, it still won't make sense. What do you mean by adding function f and g? It means that you're going to add. Let's say if f plus g acts on x, it means f of x plus t of x, right?
Right.
So the adding of functions itself won't make sense
unless the range is the same.
If the range space has no sum.
Yeah, I understand.
And here the range space has no sum.
Yeah. Yeah.
So
this is
unless
probably
the range space has a sum, you don't have you can't add functions unless you have that. So
yeah.
So maybe that bit you wrote in red.
Yeah, no, I agree. This is kind of misleading, right? Because you need to have a space where this sort of thing makes sense. The fact is that if you have the assumption of contractibility is sufficient to guarantee the existence of such a function, right? Because you can basically
of some smooth function hxt.
Some smooth function, yeah. Some smooth. Not this. Sorry, maybe I'll just erase this.
That's what the word means, that there exists such a HXT.
A smooth function that does this job, right?
That does this job. Yeah,
right.
That's enough. Yeah.
So
okay, sorry. Maybe it's not a useful thing to harp on. Okay, sorry.
No, go on. What's up?
No. What I meant is, I think it can still be salvaged in the sense that you just call the range of G to be M, but you just look. I mean, the function just. It goes to a particular point. I mean, everything else is 0, perhaps. Whether that is, I don't know. Maybe it can be salvaged.
No, but that will not be smooth. You want to smoothly.
Right.
You can't just abruptly, go from the full space to. I mean, then you could do that for any space.
Right. Okay, I agree. I take back. Yeah.
Right. So the assumption of that the manifold is contractible guarantees the existence of some smooth function that does this job.
I have a question.
Yeah.
So when you say that M is contractible, do you need even a total space or anything like that? So normally, if you have a only single manifold, you can even talk about what is the homotopy type of this manifold, right? So the way you are mentioning that Hx, capital H function, normally how you say is that you have a closed loop kind of thing on the same manifold M. Okay, and then you do the same. You have in Hx and Gx are like two different functions, and you want to contract the same loop, whether you can contract it to 0 or not. So I don't think to just say that some manifold M is contractible or not, you need a total space. You don't need.
No. That's not what's happening.
Oh, okay. Sorry. Then
that's not what's happening.
M is the base manifold, right?
The statement that M is a contractible manifold does not care about whether there are fibers sitting at over each point.
Exactly. So then that's why that Hx thing that you are defining.
Yeah.
That basically makes sense, right? You don't need M prime or anything. That's not even two manifolds.
No. What Aditya's point was that what I had written down by way of it's not it's a misleading thing, the incorrect thing in most cases to write. What he's saying is that like that sort of object does not make sense. I mean, you can write it down. What does it mean to add 2 points, right? That's the point that he's making, I think.
Okay, what I was asking is this: the Hx and Gx, the way you have mentioned Hx and Gx, if you just go up a bit. So just go up a little above. Yeah. So here you are saying that there are two maps. This H or G are basically two maps from M prime to M.
Right.
Okay. And then you're saying that are homotopic if this thing happens. Okay. And here your M prime and M are basically different.
No, right? In this example, he has the same M's.
Right. So that's what I'm saying.
In this
definition, yes.
In this definition, M prime and M are different. Yes.
Right. Exactly. That's what I'm saying. So in this definition, your M prime and M are different. But when you're talking about contractibility or not, these Hx and these Gx are defined only on M, right? Capital M.
So that's what he has done next, right? That he's studying a map H, which is from M to M.
Yeah.
And so the two maps that he has, they're both maps from M to M.
Yeah.
Right. So then H and G, this both H argument of Hx and domain of H and domain of G are both basically points on same manifold M, right?
M, and they also map into M. Both H and G map from M to M.
Right. Then what is the problem with that capital H thing that he wrote? Because these two X's are on the same manifold now.
Yeah. And the smoothness is in T. So
exactly. That smoothness is now trivial, right? That's a capital Hx is actually the thing that's correct. I think so. Because now you don't even have two manifolds in principle.
I don't follow.
Okay, wait.
So
let me write down. Let me just write this down so that it's. Let me write this down in the following way. Let me write it as H of T. I'll write this as in terms of the functions. Okay. So I'll write
Hx comma T probably.
Gt. Okay. Sorry. Gt plus 1 minus T. H, right? Yeah.
Right. And H and G are having argument 6. So yeah.
Yeah.
Right.
But what does that mean?
Yeah. So here, what's the problem here? Because X is basically uniquely defined, right? X, you don't have any problem in defining X, the domain of X.
That is not the issue. The thing is, the thing is the sum. Does the sum make sense? You can't just write sum.
Can you add points on a manifold? You can take a sphere and then write.
No, these are now functions, right? Now this Hx and Gx are just
the domain. The target of this function is again a point, right?
H is a function from M to M. G is a function from M to M. So
Exactly.
H of X is something in M. Okay, and you are adding that to X naught, which is also in M. Is M a space where adding makes sense?
Yeah, I think Aditya is trying to say that this is the problem. Right?
Why can't I have a chart and
exactly? What's the problem?
No, but even on a chart, right? You have like what is the meaning of
invariant? See, but that is not an invariant way to add things, right? See, on Rn it makes sense. Okay. But the thing is, on a sphere, it makes no sense. So the thing is, someone could say that I want to use the latitude and longitude to add. Someone else can say that I want to use the stereo maps to add. There is no invariant way of saying what it means to add.
But as long as something is there, they're homotopy.
See, no. So one second. So let's just clarify this. So if Rn is contractible, right?
Right.
So if I have Rn, this sort of thing makes sense.
Right. I understand.
Okay, because I can just add sort of coordinate wise, like what I mean, right? But what Aditya is saying is that if I have a sphere minus a point, let's say I remove the North Pole, right? What does this mean? He's asking. So that seems to be the issue, that like what does it mean to add 2 points? Because at the end of the day, g of x is a point, right? H of x is a point. So at the end of the day, you have a sum of 2 points. So what does a sum of 2 points mean?
But then if you don't have that notion, how do you define what is a smooth mapping? How do you define smoothness?
So smoothness doesn't have to mean that it can be only of
just
this
comes
form.
from the
So the thing
differentiability of transition functions.
That's all, exactly.
Yeah.
So what he said.
There's no addition construct is not there.
Yeah. So
right, that I agree.
These
But
are things that are happening at a point. Like the smoothness is a sort of
Sum doesn't have to exist. Of course, if there was a space in which there is something called a sum, then maybe this would work.
Okay, let me just try to understand. So hxt, so t equal to 0 should be gx kind of thing. So okay, so smoothness means it should be smooth. Capital H should be smooth with the argument respect to the small t, right? Or
and x and t.
So small t and x, right?
It has to go through smooth maps. Yeah.
Right. What I'm asking is that x is fine. I understand the smoothness in terms of x will be in terms of the transition functions that comes with the definition of the manifold. Then how do you define smoothness in terms of small t, which is just another parameter that you have since this H is basically M prime cross 0, 1.
Yeah, so on that full space,
that full space you will say.
So now that is now a full space, right? So now on that full space, it's a function that is smooth.
Right. Agree. Okay, perfect. Sorry. Yeah.
Okay. It's good. We cleared that up. Okay. Okay. So the statement that a manifold is contractible is sufficient to ensure the existence of such a function, right? And since these maps are homotopic, that means that H star of E is isomorphic to G star of E, right? By this theorem. Okay. But G star of E over here is simply M times F. And so what we've shown is that E is trivial if M is contractible, which is something that we saw like last time, right? We mentioned it last time. We're seeing like this is how we show it. All right. So now let us move on to vector bundles. Okay. And vector bundles are really a special case of what we've been discussing so far. They're a special case, and for example, let's consider a bundle where the fiber itself is k copies of R. Okay, so it's Rk over an n-dimensional space. Typically, what we will do is we will refer to the bundle dimension as k. Okay, if f is R bar k, we'll typically refer to the bundle dimension as k. This is obviously a misnomer, but this is standard in the literature. Bundle dimension refers to the dimension of the fiber. Okay, because that's really what's relevant when you're talking about transition functions and stuff. You need the matrices to be of a certain size and all that. Now, if the transition functions, okay, of such a bundle belong to the general linear group, right, instead of like the full group of diffeomorphisms, then we have what is called a vector bundle. Okay, and the nice thing about this is that one way to think about this is to really think of a family of vector spaces that are parameterized by points on some manifold. Okay, so to each point on the manifold, you associate a vector space, right? And as you move your point on the manifold, the vector space kind of changes and rotates into itself and stuff like that. Okay. The nice thing about this is that this construction is that the fibers inherit the structure of a vector space, which means the reason this happens is because the general linear group preserves addition and scalar multiplication. Okay, and similarly, if I replace R with C, then we have what's called a complex vector bundle. So this here is a real vector bundle. If I replace R with C, then we have a complex vector bundle. Okay, so it's really the notion of a fiber bundle is the notion of a vector bundle is really, it's like a fiber bundle. It is a fiber bundle, but the transition functions which we can choose, right? We have to choose. We have to specify what the transition functions are when we're constructing the object. The transition functions here are elements of GLK, right? The linear group, and this is kind of nice because the fact that we have the fact that the general linear group preserves the notion of addition and scalar multiplication tells us that what we can do now is we can do things pointwise. Okay, so for example, I can now add sections pointwise. So you remember that a section was essentially an object that associated to each point on the base manifold a point in the fiber, right? Now, if I have two sections, right, defined on some two local sections defined on some patch, I can define the addition of the two sections just by the following formula. And similarly, I can define scalar multiplication, right, where f is some function, right, in this way, scalar multiplication, and f is a function here, s is a section. We can define scalar multiplication like this. So everything is happening pointwise. And this pointwise is really going to be a key for us. The reason for this is that pointwise, all of the things that we would ordinarily do with vector spaces, we can do with fiber bundles as well. And this gives us a whole new set of things that we can build out of this basic definition. Okay. Another interesting thing about vector bundles is that the origin of R to the K or C to the K is preserved by GLK. Okay, so you perform GLK rotations on the origin, it stays at the origin, right? Origin preserves these. This point is preserved by the action of the structure group, right? So what you can do is you can define a global section, right? Recall that a global section was not something that was necessarily there. You could always define sections locally, right? It's not necessarily the case that you will be able to find a global section, a non-trivial global section, right? And over here with vector bundles, since GLK preserves the origin, we can actually define a global section, which is called the zero section, such that S associated to every point on the base space is 0. We just map all of those points to 0. Is this clear? So what this allows you to do, for example, is it allows you to really construct a large number of global sections. So let's say we have a section S, which is non-zero in some small coordinate patch U. Okay, and let's say that it approaches 0 near the boundary of U. Okay, so I have a section S which is non-zero in U, and near the boundary of U it approaches 0. Then what we can do is we can extend this section from a local section to a global one by defining it to be 0 outside of U. Okay, I can just declare that, like, so basically the section starts off, it's something non-trivial, but then as you get to the boundaries, it just goes to 0, and then it just stays 0 everywhere else. So now what I've done is I've really defined a lot of possible global sections, right? Just because I have this 0 section, I can sort of define many global sections. However, there may or may not be global sections that are everywhere non-zero. Okay. Is this point clear? Now, like what we've done is we've basically used this idea to say that vector bundles can have many global sections, right? But they need not be non-zero everywhere. It may or may not be, depends on the circumstances.
Madhu, quickly, can you just tell me what is global section?
A global section is so typically what we do is we define sections locally, which means I give you a coordinate patch,
yeah,
right? And then the section associates to each point in this coordinate patch a point in the fiber, corresponding fiber.
Yes.
Right. Now, a global section is something that is defined on the entire base manifold.
I see. Okay.
Okay. So there's a priori, there's no reason why global sections would exist. Okay.
I mean, you mean like can it be discussed? I mean, we have not. You didn't mention any properties about the section, right? What if it's discontinuous? Then you need it to be continuous.
Yeah, the reason you need it to be continuous is because you'll have a problem with transition functions if you don't.
Okay.
Or you'll have some sort of consistency problem you'll run into, basically.
I see. So what is the minimum requirement for a section? Just continuity, or you need like smoothness, or?
I don't think that the definition of.
I think he's just saying it's defined everywhere on the base manifold.
But then, why can't you have discontinuities? I mean, they need not. I mean, it can be inconsistent with transition functions, but the
no.
section
What am I trying to say? I'm trying to say that like. There may be a way for me to define locally a way to associate each point on the base manifold with a point in the corresponding fiber. Right. But it may not be possible to give you one single rule that will do that for every point on the manifold.
Right. So you want it to be continuous. That is the minimum requirement.
Yeah.
Yes. Not smooth, but
not
smooth maybe, but continuous. Yeah.
Continuous is what you need. Yeah.
But can you just quickly show about the SX SY, that condition that you got because of the vector bundles?
Yeah, this is just the statement that you can add them pointwise, and that scalar multiplication is also defined for sections.
So let's say I have two global. Okay, no, probably that will not work. Okay, correct.
Right.
Yeah, but I was just trying to think that whether the last statement that you make, that global non-zero global sections may or may not be there. I was just thinking that whether one can prove that. Okay.
Yeah, I mean, how does one prove a statement like that, right?
No, I don't. I thought that whether that's because you said that the first statement that you make, no. So for each UI, I can just say that my SX is non-zero, and it goes to zero at the boundaries of that each patch.
Right.
And then I was just thinking whether I can. I have a different patch, let's say U1 and U2. Then I have two different global sections for sure. If SX goes to zero at the boundary of both, so you have S1X and S2X,
right,
for U1 and U2. Then whether I can just add them and see that's also a global section or not. Not probably.
But it has to be everywhere non-zero, right? How are you going to do this?
No, I thought that whether that will work.
Yeah, the statement here is I'm making specifics here. I'm saying that there are many global sections, but I'm not making a statement here about whether or not these global sections are everywhere non-zero. That's all. That's all I'm saying.
Okay. Because a statement of that sort would have to do with what the base space is.
Right.
What are the specifics of the base space? And we have not yet, looked at that. So we would have no way of even starting to answer that.
Right.
Because
right. That's why I just tried to see what is S1, S2, that statement. Yeah, thanks.
Right. Okay. So just a few more examples. So occasionally you'll see references to line bundles. A line bundle is just a vector bundle with a one-dimensional vector space as a fiber, like one complex or one real. They're both called line bundles, and they both have one-dimensional vector space as a fiber. Okay, so you'll know, of course, you will all be familiar with tangent and cotangent bundles, which are something that we are familiar with from study of general relativity. Here, the fibers at each point are the tangent or the cotangent vector spaces, right? And for, let's say we have a local coordinate basis, what we can do is we can set up a local frame for Tm and T star m, the tangent and cotangent bundles, right? For the case of the tangent bundle, this is just given by the coordinate adapted derivatives, right? And these are the corresponding one forms, right, that are dual to them. So these guys are dual to each other. And we know exactly what the transition functions look like, right? The transition functions look like these guys over here. Okay. The point with I think, since I'm sort of running out of time, I think I have about 8 minutes left. I wanted to sort of like go into a little bit more detail about the local frames and stuff like that, but I won't do that because I think all of you will be familiar with the local frames in GR and so on. So really, the subtlety it's not very different in this case. What I want to mention is that all of the usual constructions that are associated with vector spaces, all the kind of things that you can do with vector spaces, you can take direct sums, you can take tensor products, you can construct duals. All of these things can be done for the case of vector bundles, and the idea is really that you just do it pointwise. Okay, so for example, the dual bundle is constructed in the following way. Let's say you have a vector bundle E with fiber f at some point x. Okay, then E star, or the dual bundle, just has the fiber f dual at x. Okay, so you just associate to each point x on the same base space. You associate the dual vector space, the dual vector space of f. Okay, and so that's and this will be familiar to you, that if you have a local frame for E, then there exists a dual local frame for E star, which is just defined by this relation, right? We know this from just usual coordinate kind of like, you can have non-coordinate frames, of course, in which case it won't just be a delta ij, there's something a little more complicated, you have some matrix, but you can typically get you can construct a frame in this manner. And the transition functions for the case of the, so if phi are the transition functions, which are k cross k matrices for the vector bundle E, then phi transpose inverse are the transition functions for the dual vector bundle. Okay. In the same vein, again, sort of pursuing this pointwise. Oh, sorry. I'm sorry, I seem to have like lost connection with my iPad. Yes, sorry about that. Good. So the key here is just that you're doing everything pointwise. Okay. So for example, you can consider the sum of two vector spaces, right? So for vector spaces V and W, the sum, the direct sum, is just given by pairs V comma W that are added and scalar multiplied in this way. Okay, this is a construction that we are familiar with from our study of vector spaces. And for the case of the corresponding vector bundles, all you do is you just do this sum pointwise. When I say pointwise, I mean fiber-wise, you add them. Okay, so for bundles E and F, the direct sum, or the Whitney sum, E plus F, it just takes the sum of the fibers of E and F pointwise.
So E and F have the same base space.
E and F, yeah, E and F will have the same base space, right? So for example, if the bundle dimension of E is J and the bundle dimension of F is K, then the transition functions and the corresponding transition functions are phi. Phi is a J cross J matrix and psi is a K cross K matrix. Then the transition functions of the sum are just this guy, where these entries are 0. Okay, and the dimension of the bundle dimension of The sum is just the sum of the bundle dimensions of the individual guys you started out with. Again, pointwise, you can also construct the tensor product bundle, right? And over here, I mean, we know how to construct the tensor product for vector spaces. Here, the dimension of the tensor is just going to be the product of the dimensions of the individual vector spaces, right? So really, all that I'm doing over here is I'm saying that I can do there's a laundry list of constructions I can carry out. All of them are just the usual constructions for vector spaces, but just done fiber-wise or point-wise in this case. And the more interestingly, or more physically more interesting, since you have constructed tensor product bundles, you can also do this for sub-bundles. So for example, let's say let's denote by O times P, E, just the pth tensor product of a bundle with itself. Okay, you can also construct the bundle of antisymmetric P tensors or the bundle of symmetric P tensors, since these guys are really just antisymmetrized or symmetrized sub-bundles of this over here. Okay, and the corresponding transition functions are just p-fold tensor products of the transition functions of E with the appropriate symmetry properties. Okay. Okay, good. We can also define a sort of a metric on the fiber, which is really just a pointwise inner product between two sections. Okay, and what this allows us to do is it allows us to define the length of a section at a point. Okay, this is basically just defining an inner product on the space of sections. Okay, and the in local coordinates, what this is going to look like is just like, let's say I have S and S prime, right? The inner product is mediated by a positive definite symmetric matrix Hij, and the Zi's here are really just coordinates in, let's say, Ck, yeah, this is basically the idea is that you're just taking an inner product, you're defining an inner product using this positive definite symmetric matrix Hij. You're defining an inner product on the space of sections, right? And this is called a fiber metric. In the case of the tangent bundle, if E is just the tangent bundle, right, then the fiber metric is simply the Riemannian metric on M. Okay. All right, and the reason we introduce this because later on we'll sort of appeal to the existence of such a fiber metric in order to make sense of a Clifford bundle. The reason we need to do that is because we want to define fermions on our manifold and stuff like that. So we'll need a Clifford bundle for that. Sorry, I think that my time is up. I was going to start also. I was also going to discuss principal bundles. So what do you guys want to do now? What do you suggest? It's already 11.
Yeah, it's.
I have more people now than when I started, which I think is pretty awesome. I feel like I should get props for that. There's one more person, I think. Okay.
So I'll go once you to finish, I think. That's a classic.
No, I was just congratulating him on getting not for finishing. Sorry.
So how much more material do you have? Like
I was going to discuss some constructions associated with the principal bundles.
I think this cannot be covered in a rush, I think.
Yeah, I mean, and principal bundles are kind of important because they're the basis of like gauge theories geometrically. So it would sort of be a good idea to not rush it.
Yeah, I would concur actually. Yeah.
Is that okay with everybody?
Yeah.
Okay, cool. So then I guess we can stop now.